Today we'll talk about the Otto cycle. That's the gas power cycle that's used in most gasoline engines, or let's say most gasoline engines are based on the Otto cycle. The Otto cycle is actually an idealization of what goes on in your engine. So this is a gas power cycle known as the Otto cycle. Gas power cycles employ a gas, and it's usually air because air is abundantly available. Air is used as the working fluid. There's also fuel mixed in with the air, but here we're going to approximate it as just air. And usually the air is not recycled. I mean, a cycle theoretically is where the working fluid goes all the way around and starts again. But in a gas power cycle and in a gasoline engine, for instance, the oxygen is used up when you burn the air, when you're supplying heat, and so you need to use fresh air each time. These are the cycle steps. Let's start with the blue. You have the piston up, or the cylinder completely full of air, and then you add work. You compress the gas, and when you compress the gas, you wind up with a hotter gas at a higher pressure. At that point, you add heat, and in your gasoline engine, that's done by sparking and igniting the fuel, and it gets very hot and very, very high pressure. And at that point, you allow the piston to, or the air to expand and push back on the piston, and the piston goes up and work is taken out. PDV here, work is taken out. If we look at this cycle on a PV diagram or on a TS diagram, you have at state 1 a large volume and a low pressure. As you raise the pressure, or as you push down on the piston, compress the gas, then you've lowered the volume and raised the pressure. When you ignite the gas, that's in the Otto cycle, we think of that being done at constant volume. It happens very fast, and the heat is added almost instantaneously, and the temperature shoots up, and when the temperature shoots up, the pressure goes up at constant volume, and then as you expand it, the pressure drops and the volume increases, and then you start all over again. This would be the heat removal process from 4 to 1, and you'd be back at state 1 with your original air. On a TS diagram, ideally you'd have a constant entropy work addition, constant entropy work removal, and the entropy would be increasing during the heat addition and decreasing during the heat removal steps. The combustion from 2 to 3 is modeled as a heat input. The air ejection from 4 to 1 again is modeled as a heat output. This is to the surroundings. The air goes out and cools down. You could reuse it if it had enough oxygen in it. Generally, you'll try to bring in fresh air with new oxygen. And from 1 to 2 and 2 to 3, we're treating those as reversible and adiabatic, hence the constant entropy that we saw earlier. Now we have to define a thing called the compression ratio. In piston cylinder engines, that's the ratio of the volume at state 1, or the volume when the cylinder is wide open, to the volume after the pistons push down into the cylinder and compress the air. This small volume here, V2, the compression ratio is the ratio of those volumes. A typical compression ratio for a gasoline engine would be on the order of 9 to 1. And let's suppose we had a compression ratio of 9 to 1 and that we had a maximum temperature within the cylinder after the heat addition of 2000 K. And taking the air from the surroundings at 300 K, let's determine the thermal efficiency of an Otto engine. First we have to find T2 from the compression stroke. I call that the compression stroke when the piston compresses the gas. T2 is equal to T1. Recall, for a reversible adiabatic process, T2 equals T1 times V1 over V2 to the K minus 1, and we solve for T2 is 633 K. So the work in at that point is CV. Work in equals U2 minus U1. Do the energy balance, and you'll find that work in equals mass times CV times delta T. And we're treating this using a lowercase w. Work in is per mass. CV times delta T comes out to 286 kilojoules per kilogram. Now, since we specified T3 as 2000, then we can calculate the heat added. Turns out to be 1176 kilojoules per kilogram, again using CV times delta T. For the Powerstroke, again it's a reversible adiabatic process, so we find T4 from our entropy relationship, or constant entropy relationship for ideal gases, and that comes out to 948 K. And the work out is, again, do an energy balance and you'll get CV delta T because you're looking at delta U. This is an unsteady state process. The fluid is staying in the cylinder, and so since it's not moving in or out, we have no flow work, and we'll use internal energy rather than enthalpy. Remember, with a flowing process, we'll use enthalpy to calculate the changes in energy. At any rate, we find the work that's received is 905 kilojoules per kilogram. Now the thermal efficiency is the work net divided by the Qn. So the work net is 905 minus 286, all divided by that's the work of the expansion, or the power stroke we'd call it, minus the work of the compression stroke, all divided by the heat in, and that comes to 0.53 or 53% thermal efficiency. Again, this is a very idealized cycle because we're assuming constant entropy in the power stroke and the compression stroke. Okay, so we have for constant, if we had, we can actually derive this thermal efficiency. If we had a constant K and a constant CV and an ideal gas, then we could prove that the efficiency is 1 minus 1 over R to the K minus 1. That would be a good thing, good exercise for you to prove that. So this is for our particular situation. We plug that in and we get 0.53 or 53% efficient. Now, I like to look at the cycle and relate it to an actual engine. So for the cycle above, what size engine would be needed to produce 100 horsepower at 6,000 RPM? How large of an engine would we need? So the work needed, convert that over to kilojoules per minute. 100 horsepower times 0.7457, this is a unit conversion, gets us to 4474 kilojoules per minute, and that equals the mass that we process. Let's call that m dot, even though it's not flowing. It's really flowing into the manifold, but into the cylinder and out. A whole bunch of steady state, unsteady state processes happening over and over again as the piston goes up and down. We'll treat that as the amount of air that we have to add times the work per mass. So the mass that we need to process is the work per time divided by the work per cycle, let's say, or per kilogram that goes through. So that gives us 7.23 kilograms air per minute that we need to process. Now for every cycle, for every revolution, we actually have one thermodynamic cycle. And the reason for that is, when we looked at those 4 steps in the Otto cycle, that's just processing the air that's in the cylinder. You have in a 4-cycle engine, what was called a 4-stroke or 4-cycle engine, you would need another stroke to push the air out of the cylinder, the old waste air, and another stroke to pull the air back into the cylinder. That's called a exhaust stroke and an intake stroke. Let's see, I think I have a slide on it. Here we have our thermodynamic cycle. Work in, Q out, Q in, sorry, Okay, work out from here to here, and that's your second stroke as this piston goes down. There's your power stroke. And then you have to push the piston up again to push the air out. And then you have to draw it back in. This would be the where it says air out, that would be your exhaust stroke, and then you need an intake stroke. So you actually have 4 strokes for one thermodynamic cycle. So the crankshaft has to go around twice per every thermodynamic cycle. So that's why I had that 1/2. So the volume of air processed is equal to cylinder volume times the RPM divided by 2. And I took the cylinder volume to be the mass, so this all equals the mass flow of air we're processing, RT over molecular weight times P. And our volume, equating those two, tells us that we need 2.05 liters. Gone through that kind of quick. Stop the tape, go through and solve this problem on your own time, let's say. Okay, how can power be enhanced in a 2-liter engine or any size? So I want to talk a little bit about what we do to increase our power. If we have a fixed cylinder or a fixed amount of volume, fixed size engine that we're processing or that we're using, we know that M of the air that we put through is PV molecular weight over RT, or we know this from the ideal gas equation. Anything we can do to increase the amount of air will allow us to add more fuel to burn with that air. Usually you're limited by oxygen, so we want to put as much air as we can in there into the cylinder, and then we'll get more power each time we have a firing of the fuel. So increasing the mass of the air increases the power per cycle. So to do that, we can either raise the pressure or lower the temperature. And 2 types of modifications have been made in the past to engines to do this. One of these is a turbocharger, what's called a turbocharger. What you'll do is take the exhaust gas as it comes out of the cylinder. It's slightly elevated in pressure. We'll run that through a turbine, take the shaft of that turbine and run a compressor so that we bring intake air in and compress it, and now you have a slightly higher pressure coming into your engine, and that'll allow for more air to be stuffed into the cylinder. Another thing that we can do is use what's called an intercooler. Those aren't as needed now because you can actually use, well, actually after you compress the air you will want to cool it, lower its density, and then you can actually put more air into the cylinder. Certainly, yes, you will want to do that. So you can cool the air before you put it in the cylinder. So there's 2 modifications you can make. Tons of modifications. A good engine will have lots of things to make it more efficient, but those are 2. The intercooler cools the air before it enters the cylinder. So we'll take air, and once we've compressed it, we've raised its temperature a little bit, so we'll cool it and then put it into the cylinder after it's been cooled. We'll cool it with surrounding air. Okay, a little bit on engine nomenclature that doesn't hurt to know. There's a thing called top dead center. Top dead center is when we push the piston all the way up to where it can't go any farther. Normally you have a little cavity at the top where the valves are. This is showing an intake valve and an exhaust valve that lets the air in and out. But what you do is you don't squeeze it to 0 volume, you squeeze it to, again, if we had 9:1 compression ratio, you'd allow 1 unit of volume for the 9 units of total volume. Where the piston can't reach, call that top dead center when the piston's all the way up and all you have left is that little cavity of air. Bottom dead center is when the volume is its maximum. Usually the pistons in a car engine will go up from the bottom, and the valves and the combustion chamber will be on top. The crankshaft, where the piston reaches, is down at the bottom of the engine in your car. Okay, another thing that's often referred to is a thing called the mean effective pressure. If we take work as being pressure times volume, pressure through a volume, and we take the volume max minus the volume min, that would be your stroke volume. The work of the cycle divided by that delta V would be what we call the mean effective pressure. So if we calculate for this, let's see, this cycle here, where we have all these properties, and we plug into find the net work for that particular situation, 1.49 kilojoules divided by the delta V should give us the mean effective pressure. And in this particular instance, it's 8.3 atmospheres. Okay, finally, let's have some homework. First, I'd like you to show that the efficiency equals 1 minus 1 over r to the k minus 1 for the Otto cycle. And that's for the ideal Otto cycle, where you have reversible and adiabatic power input and power output for your engine. Also look at these problems in Chapter 9. And finally, for problem 38, how much horsepower is produced by a 6-cylinder 3-liter engine operating at 1500 RPM? Do that for the data or the specifications of problem 38. And that pretty much covers this, this module.